G'day, welcome to this third video in which I demonstrate moderately speedy integration, in this case dealing with the integration by parts method. I've already produced 3 videos explaining the processes and the models and the patterns involved, and I hope you've watched those. But this is showing how to use integration by parts without substitution, just looking at the pattern. Now, these aren't the only 2 questions I'm going to do. I've got about half a dozen of them, and I'm going to try and do them at fair speed without too much talk because I'm assuming you've seen the theory in the other videos. Nonetheless, I hope you enjoy them and learn. Now, here, the more complicated function, I do know the integral of that. And therefore I can write this as x d tan x, because the derivative of tan x is x².x dx. Using now the integration by parts, I'm going to get x times tan x minus the integral of tan x dx. These swap round in the last term there. This will be x tan x minus, this will be the integral of sin x on cos x dx. We're using an identity, a trigonometric identity to help us, and here I notice the derivative of cosine is negative sine, so if I get my blue pen to show the adjustment, we'd like a negative here, so I compensate with another negative out the front. And that will give us, I've had to leave room for the second equation, so this will give us x tan x, 2 negatives make a positive, and this integral is going to give us the logarithm of cos x. There we go. I don't know how long that took, I'm not timing these, but this one here, I don't have a simple value that I can differentiate to get log x. So I'm going to put the x inside and get this, the integral of log x d x squared. Now to do that, what's the derivative of x squared? It's 2x. So I'm going to need a half out the front, aren't I? So if I can make this adjustment, then this becomes that. Now I can apply integration by parts. I get half of x squared log x minus, I'll keep the half for the other part, the integral of x squared d log x. Because integration by parts means that once we put it in a form of some function with the derivative of the other function, we have the product here minus another integral where the 2 functions swap locations. That's what the pattern is. So this will be x squared log x over 2 minus, now I don't have room to do it, so I'm going to rub out, but the derivative of log x is 1 on x. So moving the dx up here, you can see that I can replace the derivative of log x with 1 over x dx. So let's do that. This will simplify to x, so really I'm just integrating the x dx. So I'm going to get half, oh dear, I will do it. If I'm following the particular pattern I've described in the other video, I know there are different ways of integrating this. I'm going to say I will integrate to x with a half out the front feel so awful not explaining while I'm doing it, but I've had subscribers ask me just to demonstrate, so that's what I'm doing. X squared log x on 2, that's that term, minus, that's a quarter, let's put it over there, and the integral of 2x is x squared plus c. So there we go, the first two done. I hope that wasn't too confusing for you, but as you can see it was managed without substitution and following two combined fairly simple patterns. Let's look at what the next ones hold for us. Good. Well, let's now tackle these two. Here, I've just got one function here. It's a function of a function, but it's not got a product with anything else. It's already, in a sense, set up with a function with the derivative of some other function. So I would go straight to this product, x times sine log x, minus the integral, and then swap places. So it'll be x times the derivative of sine log x. Now let's see what that brings us. I'm going to regret writing this too high on the board. In fact, space is a real problem here. Well, what do we get? What's the derivative of sine of log x? Well, let me first of all put the x in place. Derivative of sine is cos, and we have to multiply by the derivative of what's inside. There we go. Now I am going to get rid of this. I haven't looked at these before. I just dragged them out of books and thought it would be worth looking at them. I want you to see how we can do them using the simple patterns. Now these x's divide out, so I've got the integral of cos log x dx. Now I hope you notice that this is not that dissimilar to what we started with. I hope you notice that. So we have a function times the derivative of some other function. So I'm going to apply integration by parts to this. And I'm going to get the product of the two functions, x cos log x, minus the integral, and we swap these two functions, x times the derivative of cos of log x, and that's going to give me x sine of log x minus x cos of log x minus is plus the integral of x. Now, what's all this going to be? Well, the derivative cosine is negative sine of log x times the derivative of the function inside, which is 1 on x, dx. These disappear, and I'm going to have to squeeze things up a little bit. I can see where this is going. Sorry. I could see it, but I wasn't even thinking. Minus the integral of sine log x dx, because these x's have disappeared and we bring the minus sign out the front. Notice that this integral and that integral are identical, and since this is negative, if I add this to both sides, I get, therefore, two lots of the integral of sine log x dx is going to be x sine log x minus x cos log x. Whoops. Trying to rush here. And therefore dividing by 2, the integral we're after I'll take x out as a common factor. Actually, I should use a bracket. That's done. We have constants spill out of this, so there should be a constant, of course, but I'm more interested in getting the functions right at this point in time. And of course, if you had limits, this constant wouldn't be a problem. But there we go. I hope you can see the benefits of setting out, and I hope, even if you might not have watched my other videos, that you can see the pattern that I'm following. Integration by parts. Let's keep going. I've got this other one that I rubbed out. We'll try it next. Well, this particular example, I can see that an exponential can pop inside here very easily because the derivative of an exponential is itself. So that's going to be quite nice. But I can see that this power is going to reduce in stages, so I'm going to get a few terms. That's just experience speaking. But let's go through the process and see if this helps you. First of all, I'll do it this way. What would I need to make this a complete derivative? And the answer is I'd need the derivative 4x to be out the front. So I'm going to put it in there and a quarter out the front. And that's going to give me this. 1/4 the integral of x squared, and now the derivative of e to the 4x. That has replaced this. If you want to check that, the derivative of e to the 4x is e to the 4x times the derivative of 4x, which is 4, and I move the dx up, and that equals that, so you can see that this equals that. I've probably already gone into too much explanation because the people who asked me wanted speed, so I will keep going. Now we have a setup ready for integration by parts, where we have a function with the derivative of another function. It's going to give us x squared times e to the 4x minus the integral, 1/4, don't forget that, minus the integral, and these swap position, so it'll be e to the 4x times the derivative of x squared. Now, I would normally, if I was doing this, instantly convert that. In fact, I might do that. It'll just save a little bit of space. What's the derivative of x squared? Well, it is 2x dx. I hope you can bear with that. So this is x squared e to the 4x on 4 minus 1/4 integral, and I'm going to, you notice that 2 over 4 is really a half, so we'll deal with that, x e to the 4x dx. So I've just multiplied the quarter by 2 to get a half. I've written the x, the e to the 4x, and so forth. Now we have something very similar, but we'll reduce the x squared down to x, and we're going to do one more step. Notice that to get this inside here again, I'm going to have to play this same game. So I want a 4 there, and a quarter out the front, and this will be x squared e to the 4x on 4 minus 1/8 integral x d e to the 4x. Same as we did up here. That's going to give us x squared e to the 4x on 4 minus 1/8, and we now do integration by parts with this integral. We get x times e to the 4x minus the integral, and they swap places again, e to the 4x dx. So that comes out to there, this goes into there and get just dx. And the nice thing now is we have no power of x at the front. So we can actually work this out. Let's do it. This will be x squared e to the 4x on 4 minus x e to the 4x on 8. Now this negative 1/8 at the front also applies to this, so I'm going to make it plus 1/8 the integral. Now, actually, let's do it. To perform this integral, if I had a 4 there, that is the exact derivative of that. So I'm going to compensate 1/8 times 1/4. It's 1/32, and the integral of this is e to the 4x. There we go. We managed it on the page. It was a particularly long question, that one. I think that came from a university textbook. I know I browsed through a few just to get some samples. The name of the game is speed, so I'll not stop and talk. Let's keep going. You can at least replay this if you want to see and study what's taken place. Got a rather interesting one coming up. Let's have a look at it. Well, this one looks tantalisingly simple in a way, because I recognise that the cosine is the derivative, basically, of the sine function. Well, it is. So I can write this in this form. Since this is on the bottom, I can use a negative index and the derivative of sine x, because the derivative of sine x is cos x. Now, I find it so hard not to explain as I go that this is a bit of an experiment, so that your feedback will let me know whether you want more of these, just to see the speed. This one, in fact, will be very easy to substitute. Let u equal sine x, but I am going to do it as it's really ideal not to do this using integration by parts. This would be so much simpler using another method, but I found it in a textbook to use integration by parts, so let's do it that way. Integrating this, we have a function with the derivative of functions, so we would multiply these together. So I'm going to write sine x over sine squared x, just putting this back in that form, minus the integral, and then swap these around, sine x times the derivative of this. Now, I'm going to do it in one step, just so we don't run out of space. The derivative of this is negative 2 sine to the negative 3x times the derivative of sine, which is cosine of x, dx. So first of all, we treat it like a power, so the power comes down, we drop one, then we multiply by the derivative of the function, we've got it. So this is, 1 on sine x minus, what have we got? Oh, bring that out, plus 2. We've got sine x on sine cubed x. Oh, let's write this. Times cos x dx. I hope you can see where this is going. I just hope I haven't used up too much board space. 2 times the integral of cos x, I'm going to put that first, and this sine divides into then leaves sine squared. Now lo and behold, same function. Now if I subtract this from both sides, I'm just trying to think. I don't know what standard of rearranging equations you comfortably handle. Let's take this from both sides, one copy of it. So we get 0 is 1 over, I'll leave it as 1 over sine for the moment, plus, now we've only got one of these left, and then if I subtract that from both sides and swing it around, we get the integral of cos x on sin squared x dx is negative 1 on sin x plus c. I should be adding constants all the way down here, which we could write as negative. Now here's where we've got to decide. In Australia and British countries, I think we would write cosec x plus c, and in the United States you would write cosec x plus c. It's just a matter of terminology. Exactly the same function. Well, that was a bit different. And I have one more. Just one. Let's have a look. Well, this is our last one. The integral of x².cosx dx. Classic setup for integration by parts, where we have a product of functions. The complicated one we can very, very easily put inside as a derivative. So let's do that. And the derivative of sin x is cos x. So that's just beautifully done. No need to adjust anything. And now, integration by parts. We multiply the two functions and we subtract the integral and swap them around. And the derivative of x squared is going to be 2x dx. So I'm going to write that now. I'm going to put the 2 out the front, leave the x here and move the sign in front. And if you look at it carefully, you'll notice that the derivative of cosine of x is negative sine x. So I want a negative here, and I'm going to compensate by having a negative out the front. So that negative sine x dx becomes the derivative of cosine of x. Then my 2x. So these two negatives actually become a positive. So I get x squared sine x plus 2 outside of, and we apply integration by parts again. We have a function with the derivative of a function. So the x cos x minus the integral of me swap cos x times the derivative of x. Well, that makes it easy. These should have a plus c at the end, by the way, but we'll just add that at the end. Probably not very right. If I've got equal signs, I should be, the instant we've done this, we should be adding constants. And going to be 2, negative 2 integral cos x dx. Now, what's the integral of cosine? That's exactly sine. So this is x squared sine x plus 2x cos x minus 2 sine x plus c. Rather a mouthful. It's more than we might have expected. I hope you can see that this solution is cleaner and neater and perhaps faster than if you were replacing with u's and v's and substituting. And I think that's what I was trying to communicate. Not that I think, I know that's what I was trying to communicate in the original video. So let's leave it at that. I hope the demonstrations have helped. You can replay them, stop when you wish and study what's gone on. And I'd appreciate your feedback. If you leave comments, I'll try and reply and clarify. Bearing in mind I'm not a world expert, but I am sharing, I guess, my experience in teaching this technique. So let's leave it at that. If you do like, please click the like button. As I said, leave your comment and I'll reply. If you're not a subscriber, then I encourage you to subscribe to find out about future videos. I'm just about to produce, in fact I've already recorded the first 3 of 100 integrals that were produced by Jim Coronius in Australia some years ago, and I know they're studied worldwide, so I thought it would be worthwhile doing that. And as always, I thank you for watching.